Should've known your love was a game. Now I can't get you out of my brain. Oh, it's such a shame that we don't talk anymore. We don't talk anymore. We don't talk anymore like we used to do. We don't laugh anymore. What was all of it for? Oh, we don't talk anymore like we used to do. We don't talk anymore. Way I did before. We don't talk anymore. Oh, it's such a shame that we don't talk anymore.
Do I get an okay from somebody?
I think that you should just give a sign to the one with the sound so they can turn on
Okay,
their microphone.
maybe.
So if you just
Thank
wave
you.
when you are ready, they will turn on.
I guess. Yeah, maybe. Okay. Should we start? Yeah. So this is actually the last session for today, and thank you for staying late. I am Ludovic, and this is a session on interactive recommender systems. So we are starting with the first paper, fast multi-step critiquing for variational autoencoders based on recommender systems.
Okay, I just don't see my slides. Perfect. Okay, so thank you for introduction and hi everybody. So my name is Antognini from EPFL Switzerland, and I'm here to present our recent work on the multi-step critiquing for variational-based autoencoder. So, nowadays recommender systems are used everywhere as they can capture accurately user preferences and achieve high performance. But the performance comes at the cost of an increased complexity, which makes them seem like black boxes to users, and that may result in distrust or rejection of the recommendation. One way to circumvent that is to generate explanations. But useful explanations are hard to generate, interact with. So for example, on Amazon, you can have some suggestions that are based on what people also bought to the item that you bought, or on Netflix, you can have like some movie recommendation based on your prior consumption. And also sometimes you can interact with items in a binary way. So for example, you can be asked to give a feedback on a movie if you're interested or not. But the problem with this kind of item critiquing is that you have to give a binary feedback. So either you like all the aspects or you don't like any of them. And in reality, you might like certain aspects of the item. So in this paper, we're gonna present to you a method that generates an explanation based on keywords, and that will allow you to interact at the keyword level. Okay, so the explanations are useful because not only the user can understand why the recommendation has been made that way, but also it allows them to critique the explanation. So let's take an example. So let's imagine you would like to go for holidays and you go to your favorite hotel booking platform. And the system outputs you an initial recommendation saying that, okay, we think that the Blue Palace is interesting because of those 4 keywords. And for some reason, you are not in the mood to go to the beach. So you say to the system, okay, I'm not interested anymore to go to the beach, please refine. And then the system outputs you another item. And this time you can see that the keyword beach has been replaced by the keyword area. And now again, you're like, yeah, but actually I would like more to be in the town and not in a resort next to the beach. So you critique again the keyword resort. And this time you have a recommendation that satisfies your criteria. So compared to prior work, I will just summarize quickly the limitations. So you have some work that are based on pure collaborative filtering that are like highly complex in terms of computational complexity and that are unstable in training. And also it's unclear how they behave for multi-step critiquing. You had some improvements to transform this framework into a variational autoencoder base that is much more computationally efficient, but still you have the same cons. And more recently, you have some linear latent critiquing that have been developed that are extremely computationally efficient for recommendation, because because it's based on linear recommendation, and that achieve good performance for multi-step critiquing because you have a linear optimization done at every step. But the downside is that the optimization is extremely slow. So the critiquing is also extremely slow. So in this paper, we're presenting a variational autoencoder, which is based on multimodal modeling assumption, and that is trained in a weakly supervised manner. And on top of that, we propose also a critiquing model that is that has separate parameters and that is trained with self-supervision. And it will allow to have fast training and fast inferences. So let's start with some with the problem formulation. So we have the user use, item I, and the key phrase K. And we would like to predict as outcome all the feedback for all items and also the key phrases of interest to generate the explanation. So the way we start to model the problem is that we would like to recommend and explain jointly and independently. So it means that we want to be able to apply the same technique to users that have not yet written reviews, like in the call start problem, but also to cases in which key phrases are not unavailable. And inspired by cross-model generation and weak supervision, we will factorize the joint probability using conditional independence. So we will assume that there is a conditional independence given the common latent variable Z. And the advantage of such factorization is that we can ignore the marginal log likelihood of missing ratings or key phrases as input. So then you can derive the standard elbow. And at the end, the remaining question is how can we optimize the scale divergence? Because we need that both observations are present, which is not what we want. So what we aim to do is to factor in the joint variational posterior using a function of unimodal posteriors. And in order to achieve that, we're gonna use mixture of experts. And we're gonna set the weights of the expert uniformly to explicitly enforce an equal contribution from each rating and key phrases that are both observed during training. But also in the case of an unobserved modality, we would like to shift the distribution, important distribution to only the rating if it's only present or only the key phrases. And this is an important factor because later we will be able to use the inference network to induce the critique representation. Okay, so in terms of training, we have multiple passes. So the first pass is we assume that both inputs are observed. So we're gonna do the standard forward pass using both input variables. But training that way, we don't train the individual network. So also we have a second pass where we train given only the rating as input, and a third pass where we do the forward pass having only the key phrases as input. And our final gradient computation is gonna be computed on those three different passes so that each network are trained jointly and independently. So now, one question remains. How can we enable critiquing? So in terms of notation, so now we are already familiar with those notation, and we would like to induce a user representation with the first inference network that I presented to you before. And now we can also induce a critique representation using the other inference network. But now the final question remains, how can we learn to the merging between the different latent representation? So here's a basic idea. We're gonna freeze our model and introduce a blending model that will be responsible of merging the different latent space together. So as the first iteration, we have, of course, only one latent representation, so one of the users. And later we have a set of critiques and a set of latent space. And the blending module will be responsible of merging all of those Z together to create this final Z tilde, from which we're gonna predict the new recommendation. So the idea is that we want to decouple the recommender model from the blending function in such a way that we will not introduce noise during training, so we will not hurt the performance of the recommender models. And also we can easily modify the critiquing model. And we will assume that each critique is independent, and we're gonna apply a linear interpolation based on the gating mechanism of GRU. So here's a question that's important. They are basically the same as the one in GRU. And now the final question is, how can we learn those parameters? So here we can use self-supervision and create a synthetic data set based on the validation set, where we are interested of, so if we have a critique, we would like that the items that contain the critique have their rank decreased or their rating decreased in the next iterations. And vice versa, For the items that do not contain the critique, we would like their ranking or their ratings to increase in the next iteration. And we can formalize those two desired data using two margin loss functions that will allow to learn that in a way that is differentiable. And we can create the synthetic data set using the validation set and sampling randomly the critique. So now let me show you just some results because we have many experiments in the paper that I cannot present here. So we conducted experiment on 4 different data sets with different properties and hundreds, thousands of interactions. And we have also different keywords that the user can interact with. So the first question that we're wondering is that how are the recommendation and explanation performance? So here, the most important is that our model has super or competitive performance in terms of recommendation compared to prior state-of-the-art baselines and also strong modern baselines. And also in terms of explanation referent, explanation performance, we have more or less a similar trend. But the most interesting experience is about multi-step critiquing. So here's a scenario that we have, through the critiquing, have to find a desired test item. So we're gonna start with an item, and then we're gonna critique some keywords using different critiquing strategy, and we're gonna do it in an iterative manner until the test item is like within the top n results. So for the session, we're gonna have a maximum length of 10, and the critiquing strategy is gonna be random based, popularity based, or most different with the user profile. And we're interested to have as metrics the success rates and the session length. So here's basically the results. So we have different model in with different colors, and ours is in red. And the solid lines represent the success rate, and the dashed lines the session length. So first, we can see that among all the models, we can find the desired item in the top 20 in like more than 50% of the time and in less than 6 turns. But interestingly, our model outperforms significantly both metrics compared to all models. And even if we assume that we train only on one critique, we can see generalized for multi-step critiquing. And also, it also generalizes for other critiquing strategies. So not only when the critique is sampled in a random manner, but also using the popularity strategy or the most different strategy. So as a conclusion, we have presented a model that is computationally efficient, that can use weak supervision, and that has coherent joint and cross generation. And also a new critiquing model that is also computationally efficient and that does not perturb the training of the recommender model, and it generalizes to multi-step critiquing. And in terms of general results, we have shown that we can have an improvement on the performance and achieve critiquing up to 25 times faster on GPU. And we can have coherent joint and cross generation even under weak supervision. So I really invite you to check the other experiment more in detail in the paper. And thank you very much for your attention.
Well, thank you, Diego, for your presentation. Is there any question from the auditory here? So there is one from Scott Waterman online, and he says, this work relies on explicit feedback on aspects of the recommendations. Do you think that there are extensions where critiques of entire items could somehow be attributed to aspects or features of the items?
That's a very good question. So I think that theoretically this should be feasible, that when we critique a feature, this has an impact on the item properties. So I guess this is possible, but I wouldn't see, like now out of my head, a trivial solution to that. But I think maybe with some Bayesian update, we should be able to modify maybe the item representation somehow to take into account a kind of updated model for the item.
Okay, thank you. Peter is asking, Peter Bozilowski, could you comment on your evaluation approach? Looks like you use data-driven evaluation, while the expectation is that an interactive recommender is assessed in a user study. How reliable are data-driven results?
True. So yeah, that's a very good comment. So here, this is an offline evaluation has done previous work for the simple reason that conducting a human evaluation is like pretty complicated and hard and required a lot of time. But this is something that we're working on to try to have like a better evaluation in the sense that reflects human behavior, because here we have conducted simulation on how do we sample the critique, which might not be how real human sample critiques. So this is something we're working on, but that's something that is hard to design and proceed. So it takes some time.
Okay, thank you very much. And the last question, what are the metrics or measurements that you use to state that you improved explanations actually?
So that's a good question as well. So it's like the same standard metrics than in recommendation, because we want to output a ranking list of key phrases. And so we can use the same ranking metrics to evaluate that. And I invite the person to check more in depth the experiment details in the paper.
Okay, thank you very much for your presentation.
Thank you.